In this session, we will discuss the slope deflection equations. So these are the equations which give rise to the slope deflection method of analysis. And this is basically a displacement based method. Okay, and as we have discussed earlier, in a displacement based method, the slopes and deflections are the primary unknowns. So we formulate the problem in terms of slopes and deflections, and then we find out, first we find out the slopes and deflections, and later on we are able to find out the other moments or forces of the structure. So let us consider first cases which are without support tiltments or without sway. Okay, so we will be dealing primarily with slopes only in this case. So let's consider a continuous beam as shown here, and we consider, let's say, two spans AB and BC. So this is something we did earlier as well for example, the three moment equation. Okay, so if we are drawing, let's say, the free body diagram of AB and BC, so there are three diagrams which we draw. So this one is the free body diagram for the member AB. This one is the free body diagram for the member BC, and in the middle here is the free body diagram of the joint B. Okay, and we will see that in slope deflection method, the joint also comes into play or comes into picture. So if we draw the free body diagram of the member AB, what we have is a moment at AB, because that is a continuous support. So there will be a moment which will be revealed. There will be a moment MBA which will be revealed. Then there are two support reactions, VA and VB1. So this will be the overall free body diagram of the member AB. And of course, as of now, both the moments and both the forces are unknown. Similarly, for member BC, we will have MBC and MCB which will show up, and we will have the shear forces or support reactions VB2 and VC which will show up. Okay, now if we draw the free body diagram of the joint at B, so if this is this dot represents the joint, so this moment MBC will come in the opposite direction on the joint B, and this member BA will come in the opposite direction in joint B. So these are the two moments which are acting on joint B, and the overall support reaction will be the VB1 plus VB2, right? So these are the two support reactions which are coming from both the spans, and on the joint both will act. So the overall summation will be the support reaction, the vertical support reaction. Okay, and we can write the joint equilibrium equation. So in slope deflection, we will see that we will repeatedly write the joint equilibrium equation. So in this case, this point B has to be in moment equilibrium, and since there is no applied moment on the joint, which means if, let's say, this is joint B and there was an applied moment here, let's say M bar, then this MBA plus MBC, which is the total moment of the joint, should have been equal to M bar, right, if an applied moment was applied. And if this M bar is equal to 0, then the total moment of joint B should be equal to 0 for moment equilibrium. Now in this case, since we will be dealing with equilibrium of a joint, we need to define a related but somewhat different sign convention for moments. So for the members, we had been defining that if it is a sagging shape, this is the positive sign convention. If the member had a hogging shape, that was the negative sign convention for moments. So which means at the left end, a clockwise moment was positive, whereas a counterclockwise moment was negative. And at the right end, a counterclockwise moment was positive and a clockwise moment was negative. Okay, so when we were looking at things from a member perspective, this was the overall sign convention. But now, since we are looking at things from a joint perspective, where there is no length, so there is no question of sagging or hogging of the joint, so we define a uniform sign convention where we say that clockwise moment at a joint at the end of a member is positive. Okay, so in a way we are saying that anti-clockwise moment of the joint is positive, which means clockwise moment at the end of a member is positive. Okay, and regardless of which direction it is. So this is the sign convention that we are defining. And of course, without loss of generality, one can assume that counterclockwise moments are positive with equal effect. Okay, so but for our derivations, we will say that the clockwise moment is positive. Now let us consider an individual span, say AB. Okay, so for AB, we will have one end moment as MAB and one end moment as MBA. And in this case, we have shown both of them in the clockwise direction because that is the positive sign convention we have chosen. And similarly, there can be a rotation at A, theta A, and rotation at B, theta B, which is there. Now, the corresponding primary structure will be something which we choose or we make where the kinematic indeterminacy is 0. So as of now, the kinematic indeterminacy is 2, and these two degrees of freedom are theta A and theta B. When we make the primary structure, we ensure that theta A and theta B are both restrained. Okay, so this becomes the primary structure with kinematic indeterminacy equal to 0. And then we will consider a few cases of loading for the primary structure, and we will add them up using the principle of superposition to derive the overall equations, right? So first we apply the externally applied load. So we consider primary structure with externally applied loads. Okay, so since this is primary structure, theta A and theta B are held equal to 0, and we have applied the externally applied load. So this is this we know that this gives rise to the so-called fixed end moments, and these are known. So these can be calculated, and we are terming them as MFAB and MFBA. And again here we are using a positive clockwise sign convention. Okay, and these friction moments can be either calculated or they can be seen from a table which are available in most textbooks. So this is the first case. Second, we retain theta B to be 0, but we apply a theta A which would have been applied or which would have been there in the original structure. Okay, so we consider the primary structure with the actual theta A applied. Okay, and this actual is of course unknown as of now. Now to apply this theta A, we need to apply a moment at A. Okay, and we have derived this earlier that to apply theta A, there is a relation between MA and theta A, and this MA comes out to 4 EI by L times theta A, right? So this is what we saw when we were deriving the stiffness coefficient, where if you put theta A equal to 1, this moment becomes the stiffness coefficient in a way. Okay, so to induce this theta A at point A, we have to apply a 4 EI by L times theta A moment, and once we do that, there is an induced moment at joint P, and the induced moment comes out to 2 EI by L theta A. So this also we have derived. So this is actually the other stiffness coefficient. So if theta A is equal to 1, this one is just KAA stiffness coefficient, and here this will be KAB stiffness coefficient. Okay, and the third case we consider is that we hold theta A to be 0, and we apply a clockwise rotation at theta B at B, and we again consider the primary structure with the actual theta B which would have been there in the original structure, and this also is unknown. Okay, and to induce this again, we will have this moment at B which will be applied to induce theta B, and this is the induced moment at A due to that theta B. Okay, so now we can consider the total moment acting at the end of end A and end B. Right, so total moment MAB will be MFAB. This is due to the fixed end moments plus 4 EI by L times theta A. This is to induce the actual theta A to the structure, to the primary structure, and this is 2 EI by L theta B. This is the induced moment due to applying theta B on the end B, right? Similarly, MBA can be written like that, and these are what are called the slope deflection equations. Okay, and these are written in a compact way in this form. Now here again, theta A and theta B are the unknowns, so thetas are the primary unknowns here. So we try to find theta A and theta B here, and then we are able to find the moments whatever are required. So let's look at an example. So let's say we have to draw the shear force and bending moment diagram of this beam shown here, and we assume a constant EI. So in this case, both ends A and C are fixed. So the kinematic indeterminacy is 1. So which is theta B is the only unknown, right? And for the span AB, since there is no externally applied load, the fixed moments are 0. And for the span BC, the fixed end moments come from that figure. So we are able to calculate. And again, we are considering a clockwise positive sign convention. Okay. So then we write the slope deflection equations. So for span AB, we write the slope deflection equations like this. And so for MAB and MBA we get, right? And in this case, since the end A is fixed, theta A is going to be 0. Okay, so in both the equations we put theta A equal to 0. And also there was no fixed end moment. So MFAB and MFBA was 0, right? So we set that equal to 0. So we get two equations like this. And then we write the slope deflection equations for span BC, right? So we get MBC equal to this and MCB equal to this. And in this case, the fixed end moments are non-zero, so we have retained them here. But the end C is a fixed end, so theta C is going to be 0. Okay, so we get two equations like this, right? Now if you see here, as of now we have so MAB, MBA, these are two unknowns. Theta B is a third unknown, right? MBC, MCB, these are two more unknowns, so 3 plus 2, 5. And right, so overall we have 5 unknowns, right? But we have 4 equations, which are these 4 slope deflection equations. So we need to generate one more equation for us to be able to solve the system, and that can be generated by considering equilibrium of joint B, right? So the moment at joint B will be MBA plus MBC, right? So this is that figure we had earlier. So if this is joint B, so there was this is MBA if this side is A, and if this side was C, there is this MBC, right? So these get applied in the opposite direction for the joint B. And when we write, since there is no applied moment at joint B, this will be the equilibrium equation for joint B. So we take the expressions for MBA and MBC from the slope deflection equations, we put it here, and we see that after this we are able to solve for theta B. Okay, and since it comes out to be positive, we know that theta B is a clockwise rotation. And then we can put this theta B back into the moment slope deflection equations to find all the moments. Okay, and again, whichever moment comes out to be positive, that will be clockwise. So this is a clockwise moment, this is a clockwise moment, this comes out to be negative, so this will be a counterclockwise moment, and this again comes out to be positive, so this is a clockwise moment. And one easy check when we are doing slope deflection method is that wherever we had satisfied the equilibrium equations, right? So we said that MBA plus MBC should have been 0, and this is an easy check where you can see whether when you calculate the numerical values, they indeed sum up to 0 or not. So once we have calculated the moments, we can consider equilibrium of the individual members. We can calculate the shear forces, right? So this is just coming from equilibrium. And then, we can combine all of that for the overall equilibrium. And once we have drawn the overall equilibrium, then we can draw the shear force diagram, right? So the shear force and the bending moment diagrams can then be drawn. Let's look at another example. So this time let's look at a frame. So let's say this is a frame which is given and we have to determine all the support reactions, and EI is again constant, right? So this A, B, C, D is a frame. Now again, for member AB and CD, there is no externally applied load, so the fixed end moments are 0, right? The kinematic indeterminacy of this system is 2 because there are two unknowns, theta B and theta C, right? Since this is a symmetrically loaded frame, there will be no sway, right? So there will be no horizontal movement of the beam at B or C. The fixed end moment for this triangular load, can be calculated like that. So for BC, these are the fixed end moments, and again, we are considering a clockwise positive sign convention. Next, we will write the slope deflection equations, right? So for AB, for member BC, and for member CD. So there are three members, so we write three sets of equations. And whichever thetas are 0, we will set it 0 right away, right? So theta A is 0 because A is fixed. Theta D is 0 because D is fixed, right? And the MFAB, MFBC, and MFCD and MFDC are 0. These are the fixed end moments which are 0, right? So overall we get here 6 equations, right? And the number of unknowns is 1, 2, 3, 4, 5, 6. So 6 moments are the unknowns, and then we have theta B and theta C as 2 additional unknowns. So we have 8 unknowns, right? So we need 2 additional equations, and these 2 additional equations will come from equilibrium of joint B and equilibrium of joint C, right? So for joint B we say MBA plus MBC equal to 0, and for joint C we say MCB plus MCD equal to 0. So these give us the 2 additional equations, right? So the last 2 equations we can solve for thetas, and we can write it in a matrix form as well. And if you really see, this matrix will be the stiffness matrix of the beam, where each of this component will be the stiffness coefficient, right? Because that stiffness coefficient multiplied by the corresponding rotation is giving the overall moment, right? So each component here is a stiffness coefficient, and it is expected that this matrix will be symmetric because of the Maxwell's reciprocal theorem, right? So we can solve for it, and we can get theta B and theta C. So what we see is that theta B comes out to be positive, which means it is clockwise. Theta C comes out to be negative, which means it is counterclockwise. Another thing is that theta B and theta C are equal in magnitude but opposite in direction, which is also expected because this is a symmetric structure. So it is possible to draw a line of symmetry at the mid of the structure, right? So everything. So this is like a mirror image. On about this line there is a mirror image symmetry, right? So whatever is the rotation at B, the amount will be equal, but the direction will be opposite for C, and which is what we get. Okay, so these are few things which you can keep checking of what to expect physically and what you are getting numerically. Okay, so once we have found theta B and theta C, we can calculate the moments. We just put all of these back, and we calculate all the moments, right? And again we can see that MBA plus MBC should be 0, right? So this plus this should be 0 because that is a joint where equilibrium was done. And MCB plus MCD should be 0, right? Because that is another joint where we did equilibrium, right? And here, because of symmetry, MAB and MDC should be equal and opposite. So we see that they indeed come out to be equal and opposite, right? And once we have done that, then we can do the overall equilibrium. So we do equilibrium for individual members, and from there we can show all the support reactions. So here you see that the vertical reaction, this 48 will get transferred like that to the member AB, right? So that is where we get the vertical reactions, and these horizontal reactions are coming because of the rotational or moment balance requirements for members AB and CD. So this will be the overall set of support reactions, and once we have reached this point, we can also draw the bending moment or shear force or whatever else is required. Okay, so let's now consider systems with support settlements or sway, right? So again, similar to what we considered for 3 moment type system. So let's say the support A is settled downwards by delta A, and support B is settled downwards by delta B, right? And now we will when we convert this to a primary structure, what we are saying is that, let's say the primary structure is shown here like AB, and the support B settles downwards by delta relative to A, right? Which means we are saying delta is equal to delta B minus delta A. So B is settling downwards with respect to A, and this is causing a chord rotation of phi, which is equal to delta by L. So this delta divided by the length of the beam, and we are able to do this because we are dealing with small deformations. So this chord rotation is in the clockwise direction. Okay, so at joint A, the clockwise rotation phi is happening because the point B is settling downwards relative to the joint at A, right? So this chord rotation phi is delta by L or delta B minus delta A by L. Okay, and since we are considering a clockwise positive sign convention, we will consider that this type of a rotation or chord rotation will be a positive chord rotation. Now, so basically we had already considered the effect of applied external loads and the actual rotation of theta A and theta B in the slope deflection equations. So we just need to see what are the additional moments which are generated due to this downward settlement in the primary structure, right? So we need to consider the additional joint moments due to delta, and this can be worked out. So again, this can be a good exercise for you to derive these. So the relation between the moment and delta. So this comes out to be 6 EI by L phi or 6 EI by L squared times delta. Okay, and if this chord rotation phi is clockwise, what will come out is that both of these moments will be anti-clockwise. So this is anti-clockwise and this is anti-clockwise. Okay, so basically when we update the slope deflection equations, we will add one more term with a minus sign. Okay, so this minus sign is coming because this moment is counterclockwise. Okay, so that is why we have this minus sign here, whereas the phi is actually positive. Okay, so phi was clockwise. So for a clockwise phi, we have a counterclockwise moment. Okay, so we update the slope deflection equations like that. Okay, so these are the slope deflection equations when we consider the effects of support settlements as well. Let's look at one example. So let's say this is a propped cantilever beam with an overhang with an end load of 8 kilonewtons, and the joint B settles by 80 mm downwards. Okay. Now, for problems with overhangs, it is usually beneficial to consider the overhang as a separate entity, right? So that is a determinate system, and the end moment here 24 and the end force 8, these can be explicitly calculated, and they can be applied as a load to the rest of the structure. Okay, so in this case we separate the overhang and we can analyze only AB, and later on we can combine it with BC. Okay, now a few things we can pre-calculate. One is EI, the bending rigidity, right? So that comes out to 1000 kilonewton meter square, and since we will need EI by 4 for this 4 meter span AB, we can pre-calculate EI by 4 as well, which comes out to 250 kilonewton per meter cube. And the chord rotation, since B is settling down, the chord rotation for AB is going to be clockwise. So we are taking it with a positive sign, and that is going to be 80 mm divided by 4, which comes out to 0.02 radians, right? So this is clockwise, and hence this will be positive. So now we can write the slope deflection equations, right? And since in span AB there is no applied load, the fixed end moments are both 0. Okay. Now since the support A is fixed, theta A is 0. So eventually we get these two equations. Okay, and now what we are doing is this MBA, which is 1000 theta B minus theta minus 30, we are equating to 24 kilonewton meter, which is the actual moment occurring at that particular location, right? So in the earlier examples, these moments were 0, so we were saying MBA equal to 0. In this case, the actual moment there is 24 because of this overhang. So we say that MBA is equal to 24, and from this we can calculate theta B. Okay, and since theta B comes out to be positive, it is a clockwise rotation. Okay, And once we know theta b, we can calculate MAB. So we can calculate the joint moment here. So that comes out to minus 3 kilonewton meter, which means that at end A there will be a 3 kilonewton meter moment of clockwise direction. Okay, and we can also get some intuition for the deflected shape. Since at point B we know there is a clockwise rotation, which means this joint will become like that later, and here it is fixed. So this is going to be the deflected shape. Okay, let's look at one more example of a frame with a sway. So let's say this is the given frame where we have to determine the moments at all the joints. Okay, now one thing we will assume here is that at the top this delta is same for both the members AB and CD, and this assumption is valid as long as we are considering the beam BC to be actually rigid, which means there is no shortening or length or increasing of the length of the BC, right? So as long as that is the case, this is called the story level deformation. So I mean, if let's say this was a multi-story type of building, right, and if in all of them we were considering actually rigid beams, then it is possible to consider one delta for each story. Okay, so if this was a 4-story building, then there would have been 4 translational degrees of freedom for this structure. Okay. Now for each AB and CD we can calculate the chord rotations. So they will come out phi AB and phi CD to be delta by 12 and delta by 18, where 12 and 18 are the lengths of each of the members. And again we see that both of them are clockwise. So phi CD and phi AB both are clockwise. So these are positive. Okay, and this 40 kilonewton is being applied on a joint. Okay, so there are no fixed end moments in this case. Okay, so fixed end moments come only because of the forces or loads which are applied on the span. So anything applied on a joint or on one of the coordinates which we are considering, they will not show up in fixed end moments. So next we can write the slope deflection equation. So for member AB, for member BC, and for member CD. Okay, so this gives us 6 equations. Okay, and our total number of unknowns, let's count. So there are 6 moments which are unknowns, right? And then we have theta B, delta, theta C. Okay, so 3 additional unknowns. So we have 9 unknowns. We have 9 unknowns and 6 equations. So we need 3 more equations. Okay, so 2 equations will come from the equilibrium of joints. So for joint B and for joint C, right? So these kind of equations we have written earlier also. So this will give us 8 equations. Now the 9th equation will come from the horizontal equilibrium of the frame. Okay, so basically there is a horizontal force being applied which is causing this drift delta. So we will write a horizontal equilibrium equation, and in general you will see that this is what will give you the additional equation. So in the direction of the drift we will write more equations of equilibrium. Okay, so we can do the individual member force balance, which gives us VA and VD in terms of the end moments MBA, MAB and MCD, MDC. And the equilibrium equation we will have is VA plus VD equal to 40, because there is a 40 kilonewton force being applied. Okay, so this gives us the 9th equation. So now we have 9 equations and 9 unknowns, and once we solve them we can find out theta B, theta C and delta, and once we have found out those we can find the end moments, all of them. Okay, so in this way you see that this is a very, very powerful method. The sign conventions are relatively straightforward, and once we get into the habit of writing the equations and writing equilibrium of relevant joints or directions, we are able to solve very, very complicated problems also in a relatively straightforward manner.